Okay, I don't need that. Yeah. I don't need to see that, or is this
Yes,
okay?
and,
I'm okay if it works for everyone.
No, it's really no problem. Both it, this is this computer. And to put got it, maybe here in the.
Can we do a single page? So when I
Yes.
Because it does this. Can you do? Do you know how to do single page?
Single page, maybe here. We did before, or here.
Fit page.
Fit page, maybe fit page. Yes, maybe.
I think it just keeps scrolling. I know it's kind of okay. I think that's okay. All right. Can people hear me? Are we good? Yes, no.
Yes, it's okay.
Okay, I think they can hear me. All right. Well, thank you for the opportunity to be here to talk to you about my research. It's always a pleasure to be back here at USM. And today I'll be talking about long-lived particles. The title of the talk will be Unlocking the CMS Experiment to Catch these long-lived particles. And the unlocking part is important for the talk because I'll try to describe how we kind of did a new technique that wasn't meant to be, the CMS experiment wasn't meant to be used in this way. And we changed that. We added a new signature on with the premise that we wanted to catch these new long-lived particles that were not thought for currently at the LHC. So neither Atlas nor CMS could do this before until we did this new development. So let me try to introduce to you now why long-lived particles are interesting from the physics point of view. So the LHC, when we try to grow these new masses, and this X is the y-axis, and we're the highest energy collisions today, so we can probe higher masses in general. And what the search, basically the physics program at the LHC has been focused on until recently is this part here. So in the x-axis, you have the proper, or the mean proper decay length, what we call C tau, or you can use that as lifetime. So the longer you live, the longer you travel. So that's kind of the, and we like to use C tau because that has to do with the detector length, as you will see later on. So in this kind of first region here, you have prompt searches. So things that get produced, new particles get produced, and then they decay right away. And then you catch the decay products of that. And then we do another extreme, which is now these new particles are neutral. They're very stable. They leave the detector unseen, and that creates missing energy. So that's on the other end, in which we're actually looking for very stable or very long-lived particles. And there is this kind of island in between, which we haven't looked for. And there is an experimental reason for that, and also a theoretical bias for that. All of that combined conspired that we left this region of parameter space unlocked until recently. So my talk will be trying to focus on how do we address this region, and is it actually fundamentally, in fundamental physics, is this motivated? Now, I have these parameters. Are these parameters actually interesting? Yeah, let's see if that actually, how long-lived particles arise, which I think is my next slide. Yeah, so in general, there are a lot of theories here, so I'm going to be careful. Now the partial width or the full width of the particle scales generically as the coupling, which is G here. I will kind of go through all of them in more detail later. Then there is a suppression of the scales between the like a heavy mediator or a heavy scale and the masses that you produce to some power. That's this scale suppression number 2. And then there is the how light is the particle or the mass splitting between particles if they're produced in pairs, for example. What's the mass splitting, the difference between these two masses? And we also call that phase space suppression. So you want ideally this number to be small if you want to have long-lived particles. So then small coupling. So I will go through one one by one, so it's more clear. So the first mechanism is simple coupling, small coupling. One example, which now we've taken again, is not the full theory, but it gives you now a sense of what we're looking for. There is a possibility for new theories in which the Higgs, so let's say phi is the standard model Higgs, it couples feebly to a dark sector Higgs, which is this phi, the red one, HS is hidden sector. And at the bottom of the spectrum of the dark sector, there are these dark pions. And these are at the bottom of the spectrum. The only way for these ones to decay back to the standard model is again through the Higgs. So they decay back through a pair of B quarks. So that's the case in which you have one small coupling here between the mixing between the Higgs and the dark Higgs. So that will naturally give you long-lived particles. Yeah. Yes, sorry.
Because this extra ion went into mixed with the Higgs and the Higgs decay.
Yeah, because typically in these hidden sectors, there is basically there's a dark QCD in there, and there are hybridization, there's like blue balls and everything. But in this case, we just take the lightest of the states. So this one cannot decay to like other dark states. So the only way to decay back to see it in the detector is through the Higgs back to BB bar pair. And yeah, the branching ratio to BB bar depends on the mass of this thing. So we scan that as we will see later. So sometimes tau tau, depending on the mass of the B pi on the pion, will be the dominant factor. So that's going to be important, and that has to do with the signature that we're looking for. The second step is scale suppression. So in this case, I take SUSY, as we all love or used to love SUSY. In this case, we have a tau, which is the partner of the tau lepton, and there is a scale suppression here in the SUSY breaking scale F, and then it decays to a tau and a gravitino. So if this is big, then you will have naturally long-lived states. So that's just one example of a generic beyond the standard model theory, which naturally gives long-lived particles. So that's the second mechanism. And the third mechanism, which I'd like to highlight is SUSY, but in this case, you can start to see what happens in the detector when you have this type of decays. So in this case, we call this again, so phase space is the last of the three candidates. In this case, the M is actually a mass difference between the chargino, which is the next to lightest state, and the neutralino, which is the lightest state. And the mass splitting between those two is very tiny, like order of like a few, maybe 1 GeV or even below, such that the momentum of the pion in which decays is very small, so it gets curled too much in the magnetic field. It doesn't hit any of the layers of the tracker, and then you have what's called a disappearing track. You have a track. This is what happens in reality, but we don't see it in the detector. So it's called a disappearing track search. And this was by no means searched for in the beginning of the run of the LHC, but it's, so we will be missing this kind of things because you're not using the right tool to discriminate signal from background. You just, maybe you're sensitive to it, but you weren't aware of that. So, okay. Does this happen in life, in real life? Yes. So actually the three mechanisms all play together to give you the pion lifetime. So people coupling, scale suppression in the W mass, and the mass splitting between the pion and the muon. So all of them working together now in this particular case, they all give you the lifetime of the pion, which is about 7 meters or 8 meters, which is the actual size of the detectors that we have at the LHC. So it's very relevant. And there is actually more than just that example. There is this region of all the particles known in the standard model, and in the same plane, mass and lifetime, in which you see a bunch of particles and states here that have sizable lifetimes that actually are now backgrounds for our searches, but they give you a sense that the standard model is a great example of fundamental laws giving rise to long-lived particles. So it's kind of, the statement I'm trying to make is that it's natural to think that any beyond the standard model theory will also possibly have long-lived particles, in the states that are produced. So therefore, we should go and look for these long-lived particles. And at the end of the day, we don't know where we are in this parameter. So we treat it as basically as a free parameter for now, and we do the best we can with the detector that we have. And what comes next?
anyway, the pion, you don't, observe this pion, because the pion interacts strongly, so it also.
Exactly, yeah. So yeah, then there are the details on how these things decay back to the standard model, which makes them different from the background. So in this case, the pion won't be a background, but for example, the decay long, which decays back to pions, that could be a background, because that, that decays back to particles in the standard model that could fake the signature that we're looking for. Okay, so that kind of introduces long-lived particles, why we need to search them, and now we go back to the more, say, experimental side. How do we cover this huge parameter space in C-tau and mass? And this is kind of a cartoon that was recently published in one of the proposed experiments. So this idea caught a lot of attention, and there are actually dedicated experiments, not only the big purpose experiments at the LHC, to search for these states, and their proposals and experiments being built in the spigots or down the beam pipe at CERN to search for these states. So for example, Codex B is near LHCb, but it's a little bit farther up, and there's more shielding, because shielding is one of the important metrics to catch long-lived particles to reduce the backgrounds as much as possible. So then obviously the funding agencies need to decide which ones to fund and what's the complementarity between the LHC main program and these new experiments. And this is kind of the understanding that we currently have. So the LHC is good, obviously, for high masses. That's what we're supposed to do. We have and we have good acceptance, and our detectors are pretty big, so we cover a lot of the C-tau range. While these dedicated experiments are either kind of close to the beam pipe, and then they try to catch very light states, or they're kind of in between, like longer lifetime but intermediate mass range. So that's kind of the niches of the searches. But the question is this, where does the boundary lie here? And I'm a CMS person, so I'll try to push this one as far as possible. So how to unlock the CMS full potential for the LLP discovery? Because this plot was made, by first principles, and at the end of the day, the details are important to draw the line where you can reach. And how far in lifetime can we do? Can we actually compete with these dedicated experiments that are meant to have the longer lifetime range? And that's kind of one of the questions I will try to answer. How low in mass we can go? Yeah, go ahead.
Which one of those experiments are already approved?
Yeah, so Codex B, it's approved. It's actually they're building currently like a prototype. I think it's called Codex Beta, and I believe Phaser as well is, and that's already kind of taking the first glimpses of data and trying to analyze it. And there is already an approved phase 2 of Phaser based on that. So, and I believe NA62 is obviously a real experiment, and then Chip, I think it's, I forgot. So I don't want to say if it's approved or not, but I don't think so. Yeah, Medusa is humongous, so it hasn't been approved, but it's supposed to sit on top of Atlas, and it's humongous. that's my summary. Okay, so how are we actually doing? This is the promise, right? This is kind of getting to the promised land. We're actually, CMS has done very well in this region, up to about 1 meter, and that's because of a simple fact that CMS has an excellent tracking system. And in order to distinguish the backgrounds, you can use the tracking system to reconstruct secondary vertices and use that as the main tool to discriminate signal from background. And typically we've done okay for masses above, say 50 GeV, because as soon as you start doing secondary vertices, if your mass is too light, then the decay, and you're too boosted because we have a big center of mass energy, then the decay products are all collimated. And if you do vertex reconstruction, that's hard because you kind of, it's just basically parallel beams. You kind of do vertex. So that's the reason why we kind of push lower and why we haven't done the full C-tau range, because we have mainly used the tracker to do that. And that's exactly these 2 bullets that I just said. So I don't have to repeat. My question is, what do we do? That's the goal. Close the coverage gaps between dedicated experiments and CMS, and how do we go and extend the C-tau range and go and to achieve that? Then the strategy is to try to do this, try to go for lower masses and extend the C-tau range. So how do we do that? Well, I guess this is the same. Yeah, okay, and then this is the history, which in 2018, we started this program at Fermilab, which is we call the LPC for the LHC Physics Center, and the LLP for LP group, in which we have a bunch of universities, including USM now, that has recently joined, to have it takes a lot of effort to build all this analysis because of the tools that you need. So it took about 2 years to get everything ramped up, to get all this analysis ongoing, what you will hear later. So we started about like 4 or 5 years ago, and we have now started to get a lot of, important results. As I said, it's a vibrant effort from maybe this is a bit older 10 institute, it might be 10, like 11 or 12 by now, and it's about like 30 people working on these searches. Okay, so now let's get to maybe instrumental part of physics. So I don't have any introductory slide for CMS. I realize that I probably should have because it's the first time, that I come here and give a talk while the university is in the collaboration, but I assume we can all, or maybe I give another talk and I give an introduction to CMS. But this is basically a projection of the CMS experiment, and I decided to keep this one because it's important for the experimental signature. So in the name of the experiment is the compact muon solenoid. And why we have the name? Because we are very good at detecting muons. That's why it was designed, and it has to do with the fact that we have this 4 Tesla solenoid field, and then we have the return to, we need to return the magnetic field, so we have to interleave the muon stations, which are the colors here, either this blue and kind of, let's go orange, gray, magenta, I don't know, and then the in the barrel section, and then the green and the blue in the end caps, and it's interleaved with a lot of steel, with a lot of material absorber in between the muon stations to be able to return the magnetic field. It doesn't play any other role than suppressing background for pion to muon with identification and to return the magnetic field. So that was the main intention. It didn't have anything to do with long loop particles when CMS was designed. But if you start looking at it and you realize that, well, it has lots of steel, that's good, again, for background suppression. In this case, it was for pion to muon with identification, but it's also good for long loop particle, so check mark. And it has 4 layers of highly sensitive active elements in between them that you can use to try to see what a long loop particle will look like when it decays there. So that will give you the handle for trying to catch the long loop particle. So that's all this region here that we didn't look at that before to try to push the high C tau range that we were kind of targeting. Yeah, the solenoid is here. It's in between. It's in between the whole point of CMS is that all the calorimeters need to be inside the solenoid. That's the technological challenge.
What do you mean by
the flux of the magnetic field? We need to reverse it here because that actually also helps the muon reconstruction because it changes the curvature between the 2 regions. Yeah, sorry about that. It's a little bit of jargon from CMS. Sorry about that. Okay, well, now, and this was the realization that we had back, I think maybe 2018 as well. Well, we first look at that picture, we see a lot of material, and again, what I said before, the devil's in the details. How much material is actually there? You have to go back to the original TDR, which is in 2006, in the revised version. The actual original one, this one, I think it's actually dating 1995. So you see here, these are nuclear interaction lengths. And again, there are calorimeter experts, so I'm not gonna pretend that I know more than that. But here you have like up to 27 nuclear interaction lengths at the end caps. That's a lot of stopping power for nuclear interactions. And that's good to try to stop standard model backgrounds again and try to discriminate signal for background. So when we saw this plot, we got excited. Like, looks like if we can see now the signal, we might have a good sensitivity or a good way to discriminate signal from background. And so we had an opportunity because if you look at the Atlas design over there, the main difference between Atlas and CMS is that in between Atlas's muon chambers, there is air. So they cannot fight the backgrounds. And when you go look at their kind of sister or cousin search, they cannot do one LLP reconstruction at 0 background level because they need to require 2 to be able to kill the background to their reducible level. while we thought we could do better by doing this, because we had the other handle, which was having more steel, more backward rejection. And that, it's a design. It was unintended. I was obviously not part of the design of CMS, but we're trying to see what the detector can do now that it wasn't planned to do that. And then the next challenge was, well, that's the signature doesn't work. What will the LLP decay look like? Okay, so that will extend the C tau range. I hope that by now that's obvious. So that's what we're going after. But if not, feel free to ask me a question. So what will happen now if we have an LLP? So the model again is this one that I described. I guess we cannot see it. Is there a way to move that? I might mess it up. So, well, maybe I just bear with me. So again, this one is the actual dark phi. Sorry, this is the set of molecules, and now we change the dark phi into this. We put it all together, condensate in this one vertex, and there's one scalar, which is the one that couples back to the Higgs and decays to the two fermions over there. So that's the decay. Yeah, maybe you can do it. I don't want to mess the whole system up. So maybe it's well, that's okay. I think we got it by now. Or I can draw it. Maybe. Yeah, so maybe we do back to what did we do here? Here. Feed the page. It doesn't work anymore. This one? Yeah. And then? That's what I did.
Presentation.
Where do you see that?
I can't see it because it's behind the thing.
Ah, yeah, it doesn't show that.
And you can drag the whole window down.
I don't think so. Okay, see, we messed it up. We succeeded. Annotate. Okay, maybe we bear with it. Where are we now? We got all the good stuff. Well, let's go back here. I think it's okay. So I think that's where we were. I can move it a little bit down, so that's okay. So yeah, this is the model. So I'm now focusing on only one of them, what it happens. So it gets produced at the interaction point, which is near 0 here. And then it travels all the way until it decays in the muon chamber. So what will happen when that goes, that was again not intended for the CMS experiment, but what happens is you can imagine that you have a hadronic shower happening in that range because it's a bunch of material, and then it acts as like the initiator of the shower, and then you have a screen of sensitive material in which you can detect the number of secondary particles. And in this case, we're using the muon spectrometer, which was intended to reconstruct muons as a sampling calorimeter. So it's a new signature, and that's what we developed. And the question is, well, does it actually do that, right? This is just the realization. It should, but do we see it when we run the simulation and everything? So this is a little bit on the gas ionization that we have, the detectors that we have as screens in the muon chambers. They are actually in each of these little color in the muon stations. There is a trapezoid, which is in this case the cathode strips, which are the ones that are in the endcaps, in which any muon or charged particle, so in this case it's muon because it was intended for that, you will ionize the gas in between them, and then you will create a hit because it has the anodes and the wires, and then you can get an XY coordinate from those two locations in the detector. So you get a hit, what we call a hit in X and Y. You could try to reconstruct how much energy was deposited, but we don't do that because it's minimum ionizing particles, but you get an XY position for every charged particle, ideally, that was in there. So that's kind of the experimental technique that we use. Now we need to do this. So once we run the full simulation, this is a bit of sorry. this was done for the first time in CMS. What we see is what we expected. So we run the simulation, we make now an LLP that in this case, we made it decay on the other side of the detector, on the right hand side. And we see now a large cluster of right hits reconstructed in the detector. And you can see also the 5 view in the transverse plane, where you also see this happening. And you realize that this line here, which I didn't explain before, that's the missing energy. So we have another handle because missing energy, typically, these are not reconstructed as particles because it's a failure of the identification system currently as implemented. And that also gives you now this big cluster and an unidentified or unreconstructed cluster of energy because you missed it. It doesn't have any tracks, right, going to it. Most of the energy goes through, and it also nothing in the calorimeters, which is what all the reconstruction is designed upon. And that's a little bit of a contrived way to say it, but it has important, say, it's relevant because that's how the trigger system was built, and that's the way you record data. So that's why I say it. So I'm not trying to say that's unique or anything. It's just important because the trigger system was built with the idea that if you don't see anything in the calorimeters, it's missing energy. And there are very important missing energy triggers in place that allow us to do the search, because it's not enough to say, well, I have this realization, I'm so smart, I figured this out, but you have to have collected the data to be able to do this search. And now the question was, do we have the data to be able to do the search? Because the detector wasn't planned for this. And if you don't put your trigger in the menu, there is no analysis, there's no fun. So this is simulation, right? So you can do whatever you want, there is no trigger. But to record the data in the experiment, you need to put it in the trigger. So the question was now, can we do this in the trigger? Maybe I have more details on the signature, but you should be thinking about, can they actually do it? So, well, this is now what we see in terms of efficiency now as a color map in the Z-axis. We try to put all the geometry of the detector in Z and R for the same signature. And you see that we have very high reconstruction efficiency, up to 90–95%, in some regions of the detector where we are at the shower max of ultronic showers. And you see some other regions in which the reconstruction goes down, and you're too far from the Muon station. Obviously, you don't see anything, but that's expected. But like up to 80–90 in some key regions, and I think the overall region, if we integrate from here to here, it's about 30%. So that's still pretty good for signal efficiency. That wasn't intended. Okay, so I need to scroll down. Yeah. Yeah, that's a background. Yeah, that's a background. But typically, since the signature is a kind of localized cluster, typically cosmic rays, the muons don't shower very often. So there is some brand for muons, but most of them don't shower. So what you see typically, it's like a straight lines in the detector, which is different from the signature, because the signature typically encompasses 1 or 2 of these stations, and it doesn't like cover too many 5 planes. So you can still distinguish it, but you got to put some special filters to remove that background. Yeah. That's a good point. This is the 1D version here, as you see, and here it's more clear that you are too deep in this field, the showers don't make it through, so you have like small efficiency, and as you're like, there is some R dependence here, that's why it's not so clear. But here you can see that it's like there's a peak, which you're at the shower max, and then it goes back again, and so on and so forth. So it's kind of interesting. We haven't fully like studied this to the last detail, but it has the right properties. So maybe if you see something interesting, it's something that we could follow up, because we haven't studied that to the fullest, because we were trying to see how good this experimental signature was. Okay, so we have that. Is it good or not? Does it cover the physics that we want? So then this is what Claudia mentioned before, maybe hinted, is that now what happens with the scalar mass? So it depends on the mass of the scalar, what final state it decays to. And as I said before, most of the signatures that we were using, typically it's a displaced jet. which is basically a particle, it hadronizes, and then it's a displaced vertex in the detector. So if you have, for example, the case to electrons, doesn't work because it's only two particles, and it's more difficult to make the secondary vertex because you need more constituents. The same for tau, because tau are difficult experimentally. They decay hadronically, they decay leptonically sometimes. So typically tau, electron, and if worse, if you decay to photons, the tracker doesn't work at all. So there's a big holes there. And what you get, probably will tell you if you have a calorimeter, is that you are sensitive to all of those, regardless of what they decay to, because photons will make an electromagnetic shower, electrons will do the same, then hadrons will do hadronic showers, and taus, you can either have the electron, it will do the EM shower, or you can have all the hadronic states do the same thing. So it's a very broad signature, and which covers all of the holes that we had before. And that's important also in the model, because depending on the masses, you will see that, and I think the projection kills it a little bit. I think I go one by one to all the areas, but maybe we skip that, I just do it in one go. You see here, this is the reconstruction for electron and photons in red. You see that's much sharper, which is what you expect, because the shower depth is smaller for EM shower. So if you're now at the beginning of the layer, then you won't make it to the next round, and it's just more peaky. And it gets up to the same level, like 90–95%. And then taus are in between, because there's some that we don't reconstruct, so on and so forth. And then hadronic is what we saw before. So there it's a proof that we're sensitive to all the decay modes besides muons. When we decay to muons, ironically, we are not sensitive because they don't shower. But if you see muons here, the region between the dimuon threshold and about 1 or maybe even less here of a GeV where muons are dominant. But in all the areas, you will expect that this search has a lot to say for this model. And I believe that's what I tried to do with the, so I go one by one. So maybe we skip that line of time. How am I doing on time?
You see that time, 10 minutes.
Okay. What's the time?
It's 3:05.
Ah, okay. So I have like 15, something like that.
45.
Okay. Okay, yeah, and this was the part that I alluded before when I was saying that's good that we have missing energy. So this is what we call the analysis, or the analogy that I made, the analysis change. You have to have primary vectors reconstruction, missing energy reconstruction, then you have to have a trigger. And at this point, most of the long-lived particles break. And then you have particle reconstruction, it's also breaking. All of the standard tools that we use for analysis just break down when you have a long-lived particle decay, because the effort that it takes to reconstruct all these things, and the fact that we have to have triggers at every step, then it could mean that you don't have any events recorded at the end of the day. So that was the main worry after we realized the signature. But this is what I was saying before, that when we have the signature, this part is not reconstructed by the main detectors and by the triggers, because it doesn't show up in the calorimeters. So it shows up as missing energy, and that we exploited that in the next slide to make it more concrete, which is this one. So this is what happens for this signature. So the main production mode is gluon fusion. You produce the Higgs, and the Higgs decays back to these two scalars, and then they decay in the muon station. But what happens, so you produce the Higgs decays right away to the two scalars. One of the LLPs makes a shower, and goes with missing energy. Let's say, for the sake of the argument, the other one, it's like the case of the past detectors, it's also missing energy, and then it makes my life easier to explain it. But for that to happen, to create a large missing energy, you have to have an ISR recoiling against that, an ISR jet. This is the blue showing the recoil, like the Higgs PT at jet level for the inclusive events, so no cuts whatsoever. And then when you apply now an ISR jet here, going back to the missing energy of 200 GeV, and you start to see that we are probing what we call the boosted Higgs regime. So it means Higgses with PT of about 100 to 200 GeV. And after that, we're fully efficient. So you would expect now, and sorry, this is jargon, but one of the main triggers at CMS, it's a missing energy trigger because of the SUSY searches that I described before. That I tried to imply that we had that assumption, but in this case, it's safe today. We have a very inclusive missing energy 120 GeV trigger at level 1. That's the hardware trigger that basically allow us to, if this were to be true, partially these events will be safe. But at the end of the day, this actually you pay a big hit, as you see here, right? But still 1% of the signal, and if you crank down the numbers of the Higgs cross section, the luminosity, you end up with about 5,000 events with the data that was collected, and that's plenty to do an analysis. So let's see what we can do with it. Wrong way. Okay, yeah, and then when we do that, so we have now the signature. So we have fixed the reconstruction. We have now a way in which we realize that these events will be recorded. So we have the trigger. So if you put all of this together, we put back, and we have fixed the decay chain, so we can do the analysis, and we're in the game. So that's kind of it. There's actually interesting things that I will discuss at the end, if I have time, is that so now that you have identified the signature, you can say, and the Muon stations are built in the level 1 trigger, in the hardware trigger. So you could wonder, can we actually now make a dedicated trigger with this new signature for the run 3, which is actually undergoing now. So I'm giving you a little bit of a hint that we're working on that, and it might be in the menu, which will be a big deal because it will allow us to recover a huge amount of data in this region, because we will not require the missing energy now. We will trigger on the signature itself if it was possible to implement that in the trigger level in the hardware that we have. Okay, so let's get to the details now, or the actual analysis. So we have demonstrated that we could carry the analysis. Does it have a good sensitivity? It promises to have that. Does it have it or not? This is it's actually the final plot. So I went from X to Y. You can ask me about all the details, and I will cover some of those, but I will just give you the upshot in this case. In this case, the main discriminating variable is, so we cluster that ball of hits in the geometrical space around the Muon stations, and then we just count how many hits, the amount of hits that are in that localized region, and that's what we call any hits. And as you can see, the signal are these solid colors. It has a long, very long tail that can go up to 1,000 hits per cluster, while the background is a falling exponential that typically dies at about 200. So it's a large signal discrimination when we go like above 200. You expect zero background. And then we do some optimization. The actual cut ended up here about 30. And at the end of the day, we expect a background of about 2 events with signal efficiency that allow us to set a limit on now. Typically, the way that you quantify this is the Higgs branching ratio to these 2 scalars. So the Higgs, that will be Higgs to invisible. The current best limit of Higgs to invisible is about 10 to 20%. So this signal that's shown here in the picture is 10 times better than that. And I mean, if you don't have to do any statistical analysis to say that that's will be ruled out. Right? So you expect this to be able to, because typically you need like about 7 signal events to rule this out if you do the statistical analysis. So here you can see in 1, 2, 3 means you have like 50 of them. So you will expect this to have sensitivity below 1%. So maybe well beyond 1%. So it's pretty good. We're probing something that normal Higgs processes cannot do by using this long-lived particle technique. So that's very interesting. And then the question is, how do you compare then at the end of the day with other long-lived searches? And we'll get to that. But maybe I wanted to not just show you a black box. I wanted to give you a few details of how the analysis really works. So there's a few handles that I didn't describe. Not everything is like, as easy or as cool as I make it sound. There are actually other handles that we have. So the Muon stations have actually a very good timing resolution, which is very relevant for what we're doing with this group. And we're doing the next generation of timing detectors. In this case, it's the Muon stations, so typically a couple of nanosecond resolution. And you see the signal being piled up in the main bucket. And you see that each bucket is about 25 nanoseconds. If you remember, the AC runs at 40 megahertz. Every 25 nanoseconds, we expect a new collision. And that's what you see here. And this is the data, which means background, most likely. So we have a control region in which we have a depleted signal region. And we look at this and you see that the contribution of the background is pretty similar in all the buckets. So that's kind of interesting because it's probably some kind of low energy background process that's dominating the clusters. But as soon as you remove, you put a cut here, my signal leaves here, I remove about factor of 5 to 10 background and I keep most of my signals. So that's one thing. Now, another thing that we do is the angle between the cluster and this variable here is the missing energy, the direction of the missing energy. And as you saw from the signal, the missing energy goes in the same direction as the cluster. And what we found, which is related to this time variable, is that all the background is kind of flat in this variable, which means that the missing energy is uncorrelated with whatever caused the cluster. So that was kind of interesting in telling you what type of backgrounds we're having, but additionally, it provides more discrimination power and a means to the background estimation because the end redshift doesn't correlate with this variable. These two curves are for end redshift below 130 and the one in these other buckets in time. And you see that they're all flat. And that allows in the experimental technique or jargon what's called a ABCD method. So you have two variables now, and this variable phi and the cluster, the end redshift. Those two variables are uncorrelated. You can take ratios and then you can predict the background in a fully data-driven way. So you don't have to do any simulation, simplifies the analysis, it gets the stuff done, basically. And that's basically what I explained here. So there is some math, but it's not too relevant. There's these two variables that are now statistically uncorrelated. If they're statistically uncorrelated, you can cut on one, and the distribution here for this one should look exactly like the one here. So if you do B over C, it's the same as A over B, and that's what this math. These are the number of hits, how many hits we see in the cluster, and the angle of that cluster of the vector, and the missing energy. So for signal leaves here. So typically the angle between the signal and the missing energy is small, and the number of hits is big. Well, for background, this is kind of flat. It's a homogeneous distribution. So for the background part, is what I just said. It's uncorrelated for the background. For the signal, it's highly correlated. that's what you want. That's perfect. And that's what we do. And this is the math to do the whole statistical treatment. If you, for the students or all the people that are interested, we can discuss the details. But it just makes a fit. But basically, at the end of the day, it's just doing that, doing A, B, C, D, multiplying and dividing, and that works out very well. And from the experimental point of view, that's great because we don't actually, this is the first time that we do the analysis. Understanding the backgrounds was going to be a major challenge. So if you find that your data shows this uncorrelated behavior, you have a method that allows you to do this background estimation without the need of understanding fully the backgrounds, just telling you what's the amount. That's not nice because we ultimately want to do that. But since we wanted to do the proof of principle, that's what we did in the first round. So we do that, probably, hopefully, and then I tell you the result. The scrolling part is a bit, yeah. So these are now the unblinded results. So first thing is bad news. I think we don't see any excess yet on this variable. So that's the first thing that you look for. Is there any excess? The blue is the expected background after we run the whole statistical procedure. And you will expect the signal to show up here. So there's a little bit, but it's two events in this tree, so not significant. And this is how it looks in the other variable, in the D5 variable, because we do two variables. Well, you see the big signal again at 1% the branch ratio, so we definitely exclude that. And then how do we quantify the final result in terms of C tau and the mass of this particle? Now going back to the original parameter space of the mass of the particle and the lifetime or mean proper decay length. I hope that's in the next slide. Yeah. Okay, so first of all, how does it compare to other CMS searches on? So this was the previous CMS searches for this light. So remember, the goal that I described was to try to go to lighter particles, below 50 GeV, and then cover larger C tau in the x-axis. This is the previous best result for 15 GeV long-lived particles decayed in CMS in green. This black one is the result from this analysis. So it's a factor of 100 improvement down is better sensitivity. That's the branching ratio of the hits to invisible. And we achieve both. We achieve better sensitivity for lighter masses. And we also achieve, now that we cover a different parameter space. You see the peak sensitivity here is about 1 meter or a few centimeters. Well, this one is a few couple of meters. And that's just because this one uses the tracker and this one uses the Muon stations. So there is a big complementarity, but also the fact that we remove a lot of background sets up the overall Y scale in this plot. So that's very interesting, and that comes from the fact that we're using this calorimeter signature with a lot of shielding. And we expect to have sensitivity down below to a few GeV and even below that. There is nothing to do with the energy, the mass of the particle, but rather with the energy that the particle decays. So there is not a fundamental limitation on the mass, but on the energy that the particles have. Okay. And this is when we look at the same model decaying now to different masses, and you see the scaling. So the peak sensitivity now, remember that we were talking about 1% branch ratio, it's actually pretty close to 0.1% at the peak of the sensitivity, 10 to the minus 3. And you see that for higher masses, the peak sensitivity is reached at a higher value, and that's because the actual parameter that's relevant for the detector is not C tau, but beta gamma. So the boost factor, because the Higgs decays to these long-lived scalars, if these are lighter, then they have more boost. So the peak sensitivity, it appears to be to the left, but it's just a fact of the relativistic factor. And it actually produces the world best results for long-lived particles decaying above 25 meters, period. That's it. And what else do I have to say? So repeat. Yeah, and it's also, as I said, one of the latest CMS results on long-lived particles. That's the only thing that I wanted to highlight here. Sorry, in this case, the important part is that it's decaying to tau tau, which was currently impossible by CMS. There was no other scalar or long-lived particle decaying to tau tau. And you see that the peak sensitivity is pretty close. The other one was around here. There's a factor of like 2 or 3 words, but it's a major improvement with respect to having nothing. This was all white before we did this when the long-lived particle decays to tau tau. Okay, so maybe I'm gonna, so I think that gives you, and then once we did this, there was a large interest from the theory community to reinterpret this search in many other models, because in this case, we focus on these Higgs decaying to 2 scalars. But we publish like kind of a lookup table. So you plug in your model, you tell me where it decays, what energy it had, and I will tell you what's the efficiency of reconstruction. So you can reinterpret in your favorite model without the need to redo the whole analysis. So we work with a few theorists, we provided help and input with them, and there are 2 papers like being published or already published with this data, using this data that we provided and interpreting in a wide variety of models. And some of them are actually from around. It's Juan Carlos Elo and Giovanna Catin. They took this input and they interpreted this in a heavy neutral lepton model. The other one is Michele Papucci from Caltech, which was there before, so we had some connections, and he interpreted in a wide variety of models that were not interpreted by CMS before. So with that, that's basically this few slides. So I will skip that in light of time. These are all the other models. Yeah, and then I will go back to the more experimental part that I described before, which is I hinted to it. Yeah, so it's kind of whatever. So the fact that now we have the signature, and one of the limiting factors is still, if you remember when I said we pay a hit of 100 times when we require the missing energy trigger. And in that part, I spun it in the way that still a lot of events, but obviously we will do much better if we have a dedicated trigger and now uses the signature. The challenge was, can the hardware, the FPGAs, the backend, everything that's built in the Muon stations, can they handle this new signature at the hardware level without changing the detector? And the short answer, yes, with some limitations, but mostly we keep most of the sensitivity of the signature itself. We did all the work to put this in hardware. If you're an experimentalist, that's a lot of effort to do that. It's a lot of effort to now change the firmware on the whole detector, which you're risking for the whole detector now to not work for muons. So you need to convince a lot of people that that will be okay. So we managed to do all that, we did all the work, and we put this in the new trigger. This trigger has been taking data last year in 2022. We collected about 40 inverse femtobarns with this new trigger. And what we expect from this new trigger is about a factor of 20 improvement. So this is with the missing energy trigger. This is what the new trigger will give you. That's the acceptance of the same model as a function of C tau. So we got a factor of 20 there, improvement that we will be able to start analyzing very soon. There's a search ongoing now with this new data, but since new data, new trigger, we have to do a lot of validations, but there is a promise that we can improve upon the best result about a factor of 10 to 20. So that we're very excited about that, and there's a big program that we're following upon that, because now we don't rely only on the Higgs to have the recoil to have the signature. We're triggering anything that will produce a signature. So it will be more wide, a more, say, catch-all signature when there are long-lived particles. This is the expected sensitivity when you look at the limit clock. If you just do a back of the envelope, if we are able to keep the backgrounds at bay, which is a big if, but if you do that, we go from this blue line to here. So that's a factor of 10 improvement. So we start probing like 10 to the -4 branching ratio of the Higgs to this scale. So we're getting into interesting territory, and we're able also to do this at very long C tau, which was the ultimate goal. And yeah, before it's too late, the next generation for what we're trying to do, this is for run 3, but in run 4 or the high Lumi LHC, now we'll have new detectors, new dedicated detectors, which again will be different between Atlas and CMS. And this is again unique for CMS, is that we will implement a new timing layer in between the tracker and the calorimeters in here, in both in the barrel and the endcap, that will give you a time resolution, a precision on the arrival of time of charged particles of 30 picoseconds. So it's the first time that we put this detector, large scale detector, in a collider experiment with this kind of precision. So for each track, you will get a timestamp with a precision of 30 picoseconds. And as you already saw for the Muon station, that had a big impact on the reconstruction of long-lived particles. And that had a resolution, which is about a factor of 30 worse than what we have now. So we expect this to be a massive improvement for long-lived particle reconstruction. And it's something that we are actively working in here at USM. These are actually the results that show that we can achieve now with these sensors. There are 2 different technologies in the barrel. We have a scintillator and a SIPM, a silicon photomultiplier. And here we show that we can achieve 25 to 35 picoseconds. And in the endcap, which is the relevant part for USM, is that we're using this called low gain avalanche detectors, which is a silicon detector with gain that allows you to get about 30, in this case, 30 to 40 picoseconds, but these are all fine. We now can achieve, Claudio has done some awesome work in which he achieves 25 picoseconds with a much newer technology. So this is all going in. We passed what's called CB2 review in the US jargon. So this is going ahead, and it will be installed in CMS, and we'll have this new tool for reconstructing long-lived particles.
Open the detector.
Yeah, we will actually also replace some of the calorimeters because the whole endcap, electromagnetic and hadronic, will be thrown away. It will be replaced by a new sampling calorimeter, which that's supposed to happen. It depends on the detector. That will happen in 25 to 27. Yeah, so we'll take data until end of 24, and then it will happen between 25 and 27. So it's we're rushing. We need to get it done. We need to start. And there's a test team actually in April we were discussing right before, to send some of our people there to participate in these test teams that will start to commission these modules with the full sensors. So and I just to connect the dots, right? So you may seem like this connection between long-lived particles and timing. It's this ad hoc, because we're doing long-lived particles, we're doing timing, but it's not like that. This is actually a plot of the same model. This is what we will gain, again, a factor of 10, if we now do the displaced reconstruction with the tracker now. So remember, this will be installed between the tracker and the calorimeter. So it's not the same as a Muon station, but it's related. And now and the problem also for the tracker experiments or the tracker-based systems is that they also have difficulty in triggering because they have to raise the thresholds in masses. So they are not sensitive to lower masses. Typically, you have a HT, which is the hadronic energy kind of stuff. But now you use timing as another handle, independent of that. You can lower the threshold and then have access to lighter states. And these are basically, we found the sweet spot here in terms of signal efficiency, which is about 10%. Maintaining the trigger rate is the function of the trigger rate. So it's a bit tricky. You can ask me more details. But this blue one is kind of the sweet spot. And that actually constitutes about a factor of 10 increase in signal efficiency, similar to what we achieved with the Muon signature now, but for tracker-based signatures. So that will be a big deal for what we call phase 2 or the round 4 of the LHC. I think it's the same, and then I have my outlook. Okay, so we're CMS, and in particular, our group is heavily advancing the LLP frontier now with run 2 data, this result that I showed you. We will do that with the new triggers in run 3. The trigger that I just described is my work. There are other triggers in place to try to catch more longer particles. And we will continue to do that at the high luminosity, which is run 4. So there is still a lot of work to be done instead of instrumentation, detector sensor, triggers, and edge processing to try to catch these longer particles to get the experiment ready, the detector ready to trigger on these things and do the reconstruction. And our group specifically is what I call vertically integrated because there's many steps. You need to define the signature, you need to define the trigger, you need to have the know-how on how the detector works, you need to have the know-how on how the reconstruction works. These are not standard signatures, and it's a big experiment. So you have to be able to do all of those things in one small group with about 20 people. So you need to know everything for your signature. But at the same time, that provides a great opportunity for you to do impactful work. In particular, it's a good opportunity for USM to continue to lead detector R&D, in this case with precision timing, and also enable new cutting-edge science with physics results using those detectors now on the long lived particle domain. And I consider this, and I discussed with some of the people at CMS, designing the physics program, that they see this part as an integral part of the physics program of CMS, and therefore will be, there's a decade ahead of us with new results, challenges in detector, and also on analysis. So that's all I got.
Thank you very much for the very nice poll. Question from the audience. I have a couple of questions.
Yeah, go ahead.
You have concentrated on mostly on the hits.
Yes.
And obviously, there's a lot of data that is not the hits.
Yeah.
And there, obviously, you can also, I suppose, see different models. And
Yeah, so there's actually one, I have just one example. Again, I don't pretend to know all the possible models, but I know that at least some of the people in the audience are interested about heavy neutral leptons, and I mentioned it pretty quickly, and it was maybe rambling. So there is this model, for example, that we have recently. This one I cannot show you because it's not public. I can only show it to Will and some of the CMS people. But basically, in this case, it is a heavy neutral lepton, and it's a bit different. The heavy neutral lepton of the neutrino. So the W gets produced, it decays to a neutrino. The neutrino mixes with the heavy neutral lepton, and that provides neutrino masses and solves another problems of the standard model. And because of, again, it has to mix it back to the standard model neutrino, to an off-the-shelf W, so on and so forth. I think I have made the diagram here. That naturally, again, gives rise to longer particles. So the heavy neutrino has been searched for in prompt searches too, and typically those are for higher masses. But again, the low mass region was neglected because there's acceptance or there's too much background because they need to fight standard model backgrounds with lower masses. But if you now add the longer particle as a handle to fill the background, you can maintain that. So what we are looking here is now the immune shower system, the one that I just described, if you look at it, that's basically the best sensitivity, projected sensitivity for masses between about 1 to 5 or 6 GeV for heavy neutral leptons. So that's an example of, without changing anything in the analysis, what I did here was just doing a simple calculation, acceptance, maintaining the same analysis without changing anything, just triggering a different thing, which is a lepton, because it will produce a chrome lepton, then you achieve the best result for a mass. And it's something that we are not very good at doing. In this case, the experimentalists, typically we try to do something that's very generic, and we hope that the theories or the phenomenologies.
For example, with respect to supersymmetry.
Right.
People have already mentioned that most of the supersymmetric parts are
Yeah, I don't think that's true.
And even they have candidates for that matter, so raise particles and all those. And those are being ruled out already. So a lot of these particles, not new particles, are being ruled out already.
I don't think that's true. That's a claim. Yeah. They basically assume some of the parameters, for example.
What's in your model?
Yeah, and it's so big that basically all these models have been neglected before, and that's the first time we're looking at it. So when you compare these searches compared to the previous ones, this is about an order of magnitude, 2 orders of magnitude more sensitive. So there is still a lot of things that are not ruled out, and I mean, obviously we have ruled out more than what we had before when we turn on the machine, but there's a lot of spaces that we haven't looked, and so this is kind of addressing one of the models or other models out there, but the Higgs was a natural one because that's what we're good at producing. So
Yeah, when I have this model, I would say if you want to consider Higgs and produce a Higgs, you will try to find the experiment in which the Higgs produce as a resonance.
yes,
And then you need an example. Proton collisions in which you have more or less a refractive interaction.
Higgs
You
factor.
measure the 2 protons in the final state, and you know the missing energy experiment, and you're going to see a bump.
Yep.
Why not?
One.
We're going to see another bump, several bumps.
Well, the problem, I can give you the political answer, which is
It's a very nice experiment.
these full projects have been approved for so long.
It's the same, it's similar to electron-positron in the
So there are proposals like that, but the LHC is taking all the resources in the forward direction. Yeah. So they need to be.
See, that's what the whole thing. The only thing you need is.
Yeah.
More question, comment?
So your C tau parameter is basically your C tau is a little bit inside of your detector.
Roughly, there's a bit of caveat, but yeah, you can think about it like that.
But then when the particle is faster relativistic, it lives even longer. So what happens?
Right, yeah, so that's what I kind of tried to hint on this where's that plot? A few slides back. It's when I show the masses here, yeah. So that, I mean, it's a bit convoluted, but I think I can make the point. So this is the higher mass, the blue one, 55 GeV. And then this is the lighter mass, which, so since they come from the Higgs, the 7 GeV is more boosted. And it typically is like the mass of the Higgs is the difference is mass of the Higgs over this. That's kind of the factor. And you see that in the C tau range, it may appear like this one has a smaller C tau because of the boost factor. So we see that, yeah. So for lighter masses, it looks like we were using the tracker, but it's not. Yeah, we're using the Muon stations, but it's the relativistic factor that gives you that. Yeah.
More questions?
Question from the audience in Zoom. Since the audience in Zoom, the questions? If there are no more questions, we send the speaker again for the next talk.